So this is the fourth session for P6 radioactive materials for the OCR 21st Century Science Physics units. In the last session we looked at alpha decay, and this one we're going to look at beta decay. So beta decay. So in beta decay, what happens is that one neutron inside the nucleus of an unstable isotope suddenly changes into two other particles. It changes into a proton and an electron. Now, this is feasible in as much as an electron has got a negative charge and a proton's got a positive charge. So if you combine those together, you'll have something with a neutral or no charge. And the fact that the electron has hardly any mass at all means that there isn't too much of an issue about accepting the idea that the proton contains most of the mass, which is the same as the neutron, and the electron has a tiny bit extra. So you have to accept this instantaneous change of a neutron into a proton and an electron. So the electron is ejected from the nucleus, and the electron is known as a beta particle. So in that sense, a beta particle is simply an electron, but the news is that the electron comes out of the nucleus, which is quite an odd thing to think of. However, that's what we've got. The neutron changing instantaneously into a proton-electron. The electron gets ejected, and the proton stays right where it is in the nucleus. So let's have a look then at the decay equation for beta, because it can be slightly confusing. So we take carbon-14, which is something which undergoes beta decay spontaneously, and what happens is that a beta particle is given out, and then we've got to think about what happens to our mass number and our proton number. So if we think about it, we've got 14 particles in the nucleus. That then jumps up to 15 particles because we've got one particle turning into two, but one of them is ejected. So effectively the neutron disappears and is replaced by a proton, and the electron goes out as the beta particle. So essentially the beta particle replaces the lost neutron. So in actual fact there are still 14 particles in the nucleus. Nothing's changed. And if we think now about what's happened to the number of protons, well, to start with, there were 6 protons in the nucleus. But now, because our neutron has spontaneously changed into a proton, then the number of protons actually goes up by 1. It goes up to 7. Now, if you look in the periodic table, 14(7) is nitrogen. So in the decay of carbon-14, carbon-14 is an unstable nucleus which ejects a beta particle and then turns into nitrogen. So the numbers for the beta particle may look a bit odd. Remember that we have to make sure our mass numbers balance and our proton numbers balance. So the only way we can have that balancing is if we have 0, and then this one becomes -1. Because remember, this is the number of protons that are being ejected in the beta particle. Now, -1 protons is effectively an electron, because an electron is the opposite charge to a proton. So that is the symbol of a beta particle. It's also the symbol for an electron. So sometimes it's written just as E0 -1. That's another way of writing a beta particle, because a beta particle is an electron. So in beta decay, the beta particle, or the electron, is ejected. The number of particles in the nucleus stays the same, because one neutron is less and one proton more, and the number of protons goes up by 1 simply because a new proton appears. Okay, so if you look at the properties of beta particles, they are slightly different to those of alpha, but again, they need to be memorized. So the range of beta particles is a little bit further, up to about 1 meter in some cases, so 15 centimeters on average in air. And it's important to remember it's the range in air. The range in a vacuum will be much more because there's nothing to collide with, nothing to lose its energy. And so the range in air around 15 centimetres. It's stopped by very thin metal such as aluminium. So thin aluminium is what can stop it. So it can pass through paper, can pass through skin, but needs a thin piece of metal to stop it. Obviously its charge, because it's an electron, is negative. Now it's also an ionizer, but its ionizing power is slightly less than an alpha particle, simply because it's a lot smaller, and so it's a weak ionizer. And again, these points have to be remembered as the facts about beta radiation. So again, beta radiation has got lots of uses. We'll come on to uses later on. And remember, this is a spontaneous thing that happens. Nothing triggers it. Nothing can stop it happening. It's just that a carbon-14 is destined to decay into a daughter nucleus, which is nitrogen, and give out a beta particle. And again, it's a random process. It's unaffected by temperature. So if you heat it up, cool it down, these nuclei will eventually decay. And we'll come back to the properties of beta later and how it can be useful to us.